We're going to shift gears completely when we move back to chapter 3. Section 3.1 is called radian measure. First we have a definition. An angle that has its vertex at the center of a circle is called a central angle. Okay, so they mention a circle, so there's a circle. And an angle that has its vertex at the center, okay, so we have the center of the circle's important here. And an angle, there was the first definition, a second definition we did in the course. An angle, remember, has a vertex, an initial side, and a terminal side. So for example, if I have that as an initial side, you rotate a certain amount, say like this, right? Remember, an angle had an initial side, a terminal side, and a rotation. So this is an angle whose vertex is at the center of a circle. This is called a central angle. So when you hear central angle, you're thinking of, it involves a circle, obviously. Okay, now I'm going to draw a couple of pictures here, so don't draw it in your notes yet. Okay, let me draw a circle here. Okay, of a certain radius r. Okay, let me use sort of the same picture I had right here. Let me draw another radius out here. So I have two radii, obviously both of length r. Now, think about the arc length that these two radii intercept. So the arc that they intercept is here. How does the length of that arc compare to the radius? Well, it's clearly bigger, isn't it, right? This distance is a lot bigger than that distance, right? So the arc intercepted by, the angle here, you want to think of this as a central angle. The arc intercepted by the central angle is bigger than the radius. Likewise, again, don't draw the picture yet. In this picture, imagine an angle like this. So there's r, two radii, right? And I have a central angle here with rotation. Now, let's look at the arc intercepted by this central angle. How does the length of the arc here compare to the radius? Well, it's smaller. So notice I tried to draw the pictures with about the same radii. Notice here I have an angle where the arc length is bigger than the radius. Here I have a central angle whose the arc length intercepted is less than the radius. So somewhere there's an angle in between this angle and this angle where the arc length is equal to r, isn't there? So that's the picture I want to try to draw. So try to draw it the same in your notes too. So here's a circle, here of radius r, and I want to draw a central angle here such that the length of the arc intercepted by the central angle has the same length as r, right? This was bigger than r, this was less than r. So there has to be a place in between where that's not a very good circle, where the length of the arc intercepted is equal to r. That's a little better. Okay, so where does that look like that might be? Maybe here? That's still not a very good circle, but right, so I claim that the length of the arc here is equal to r. I know I can do it because this was too big and this was too small, so somewhere there's a place in between. So I claim that this angle right here is the angle I want, that central angle. So the second definition here says a central angle, this one, that intercepts an arc on the circle equal in length to the radius of the circle has a measure of 1 radian. So this angle right here is 1 radian. Now, unlike when we did degrees, remember when we defined degree, we said all the way around is 360 degrees, right? We were told what 360 of them were, and you had to imagine how big one of them would be. Chop this up to 360 pieces, that's 1 degree. Notice here we're taking a different approach. There's a picture of 1 radian. Okay, so get that in your head, right? 1 radian is that much. Okay, so obviously 1 radian is a lot bigger than 1 degree, right? Because 1 degree I can't even draw. It's too tiny. Okay, but 1 radian looks about like that. Okay, so to get to the next topic here, let me add to my picture that I've already drawn there. Don't add it to yours, because I want you to have the picture of 1 radian where it says what 1 radian looks like. But suppose I added to this picture. And suppose I drew another radian next to it. Again, this is not perfect, but okay. So now I have an angle of a radian, and together that's 2 radians. Well, how long is the arc intercepted by that angle, central angle of 2 radians? Well, from here to here is r, because that's 1 radian, and that's 1 radian, so that's also r. So notice 2 radians, a central angle of 2 radians intercepts an arc of length 2r, doesn't it? Right? 2 radians cuts out 2r. What if I did 3 radians? Right? 3 radians, I'll put another one here. That would intercept an arc of length what? 3r. What if I did half a radian? So what if I get rid of this? Right? What if I chop this in half and take half a radian here? What would that arc length be? A half radian intercepts an arc of length what? It'd be half r, wouldn't it? Because from here to here was r, and I took half of it. Right? What if I took square root of 2 radians? Intercepts an arc of length how much? Do you see the pattern? 2 radians intercepts 2r, 3 radians intercepts 3r, half a radian intercepts half r. Square root of 2 radians, which is somewhere in about here, would intercept how much? Square root of 2r. Do you see the pattern, right? It's just multiply the amount of radians by r. So let me do another one. Suppose I had 2 pi radians. Okay, 2 pi, so a little more than 6 radians, about 6.28. 2 pi radians would intercept an arc of length how much? Well, it'd be 2 pi r, wouldn't it? Right? However many radians you have, you multiply that number by r, that'll give you the arc length, right? So 2 pi radians intercepts an arc of length 2 pi r. But what's 2 pi r? In any circle, 2 pi r is the circumference. Right? You should know the formulas in a circle. Area is pi r squared, and the circumference is 2 pi r. Or pi times diameter, right? 2 pi is the diameter. Okay? So 2 pi radians cuts out an arc length of 2 pi r, but 2 pi r is all the way around. Which means 2 pi radians is the central angle all the way around. Which tells me that 2 pi radians is 360 degrees. Okay, so let me say that one more time. So 2 pi radians, however much that is, intercepts an arc of length 2 pi r, but 2 pi r is the circumference of the circle, so that's all the way around, which means this angle 2 pi radians is all the way around, which means 2 pi radians is 360 degrees, or if you divide both sides by 2, you get pi radians is 180 degrees. That's our conversion factor. So the whole point of this discussion was to figure out how do we convert from radians to degrees and vice versa. Okay, so that's what the next part is all about. We're just going to do some examples. Now, remember when we were converting degrees and minutes and seconds? I went into a lot of gory detail there to explain unit conversion, so then I wouldn't have to do it here. We know how to do it now. So it says, convert from radians to degrees or vice versa, give exact answers. I mean, don't punch in the calculator. So 2 pi over 3. Now it says convert from degrees to radians or vice versa. What units is this in to start with? Now hopefully you said radians. Now let me ask the reason why. Why is it, how do you know this angle I've given is in radian measure? Okay, now the answer is not because there's a pi in the problem. You can have pi degrees. It's a little more than 3 degrees, right? So that'd be real small, right? That's too big. Right? Pi, you can have pi degrees. It's not the pi that does it. What is it? There's no degree sign. Okay? When you mean degrees, you put a degree sign. If you leave off the degree sign, if there are no units listed, that means radians. So if you want to write RAD next to it, that's perfectly fine for radians. But if you leave off the units, that means radians. So if you write 20 and you mean 20, if it's 20 degrees and you leave off the degree sign, you're telling me 20 radians now. So units matter, okay? You need to be really careful with your units. Okay, so if you want to put in radians, you can. Now, what was the procedure of unit conversion? I have radians up here in the numerator. I want to get rid of them, so I'll put them in the denominator, and I want to go to degrees. So this is what we did before with degrees, minutes, seconds. So the radians cancel. I'm going to degrees, And then you focus on the units first, then ask yourself, how many degrees is how many radians? 180 degrees is pi radians. Okay, so when we do the multiplication, now the pi's drop out, and the radians drop out, they cancel, so I get 360 over 3, that's 120 degrees. Don't forget your degree sign, right? I'm going from radians to degrees, so don't forget your degree sign. So the only, we know how to do unit conversion, we did it before, so the only new thing is 180 degrees is pi radians. The next one, B, says negative 270 degrees. Again, I'll put it over 1 to make it look like a fraction. All right, go ahead and put your units and your numbers in there first. I'll give you 10 seconds to do that. Okay, so the degrees go in the denominator, the radians go in the numerator, because I want the degrees to cancel, and pi radians is 180 degrees. Okay, and so the degrees cancel. Notice the pi's cancel here. Pi over pi is 1. There's no pi to cancel, so we keep the pi. So it's negative 270 pi over 180. Now I expect you to simplify your fractions. 90 goes into both of those. That's minus 3 pi over 2. Again, you don't have to write radians at the end. If you want to, that's fine. Okay, so that's that one. The third, C, says 315 degrees. 315. Pause the video and see if you can do that one on your own, and then I will do it. Okay, so 315, let me think of that as over 1. Right? I want to get rid of degrees. Degrees in the denominator, radians in the numerator. Pi radians is 180 degrees. So when I multiply, the degrees cancel, I get 315 pi over 180. Now what goes into both of those? 45 goes into those. That's 7 pi over 4, I believe. Again, you don't have to write radians, but if you do, that's fine. Okay, so hopefully you got that one right. And then the last one here is 1. 1. Now what is that? 1 what? Well, there's no degree sign, and therefore that's 1 radian. Okay. I've put problems like this on an exam before, and I've had students on the exam, when they saw the 1, they said, well, they added a degree sign for me. They changed the problem for me. It's very nice of them to do that, but that wasn't the point of the problem. So 1 radian is what we're looking at here. Okay, so the conversion factor, radians on the bottom to get rid of radians, degrees on top, and 180 degrees is pi radians. Now notice the radians cancel there, but the pi doesn't. There's no pi for the, up in the numerator for pi to cancel, so it's 180 over pi degrees. And again, the instructions say give the exact values, and so just leave it alone, 180 over pi. Now, I mean, normally on a problem like this, the exact value, I usually like exact values, because if you want to get a rounded answer, you can just type it in. If somebody gives you a rounded answer to 2 places and you need it to 4 places, that doesn't help you. But the point of this problem was, I want to go ahead and punch it in anyway, just to see how many degrees is 1 radian. 180 divided by pi is about 57.295, so 57.3 degrees. So remember that original picture I had of the central angle, with the R and the R and the R? That angle is about 57.3 degrees. But remember, it's 1 radian. Okay, so again, in this problem, I made up the problem so we could actually see the 57.3 degrees. That was the point of the problem. The exact answer would be this one right here. Now, it shouldn't surprise you that we're really going to be interested in radian measures of angles in our special triangles. Now we did all that with degrees, but what were the interesting ones that we can? The 30 degree, and I write 3 again. The 30 degrees, the 60 degrees, the 90 degrees, and the 45 degrees. Those were the angles in the special triangles. So if you do the conversion to radians on these, think about it. 180 degrees was pi radians. This is half of 180, so that's pi over 2. 45 is half of 90. It's half of that, which is pi over 4. Right, that's easy to kind of think of. If you do the unit conversion, 30 degrees is pi over 6, and 60 degrees is pi over 3. Notice, if you do it, I mean, the product is always 180. 30 times 6, 60 times 3, 90 times 2, 45 times 4. But these are ones you probably just want to memorize. But this is easy. There's a 3 and a 6. So if it's 30 degrees, it's a 6. If it's 60 degrees, it's a 3. Again, pi radians is 180 degrees, so half of that, 90, would be pi over 2. But these are ones you probably just want to memorize. Okay, now what we want to do, I want to get you to try to think in terms of radian measure. In the next chapter on graphing, everything is done in radians. So you're not going to be able to sit and convert every time a radian measure angle comes up. Okay, so the next example says construct angles with radian measures of 10 pi, 3 pi, minus 2 pi over 3, and 5 pi over 3, without converting to degrees first. Okay, so the whole point of this is to get you thinking in terms of radians. Remember, all the way around was 2 pi radians, halfway around was pi. We're working with the irrational number pi, which makes things complicated, but all of these have a pi in them, so that shouldn't be so bad. Okay, so 10 pi radians. What's the way to think about 10 pi radians? All the way around, one complete revolution is 2 pi radians. So that's 5 of those. So 10 pi radians is just 5 times around. 1, 2, 3, 4, 5. Done. Okay, so if you think of it that way, it's not so complicated. Right, 5 times around would be 10 pi radians, and there we go. Okay, let's do 3 pi radians. Well, how do you want to think of 3 pi? All the way around is 2 pi, so that's once around at least. 2 pi. Now, how much is left to go? I still have pi radians to go, which is halfway. So there's a picture of 3 pi radians. Okay. What about minus 2 pi over 3? Now, here's the way I think about this. So a negative angle means we're going to be coming down. We're going to be going clockwise, right? All the way to here would be negative pi. I think, when I see this, I think of this as minus 2/3 pi. Think of it that way. Instead of 2 pi over 3, think of it as minus 2/3 pi. So we just need to go 2/3 of the way. We're just trying to get a rough sketch here. I'm not trying to make it perfect. So just 2/3 of the way to here. Well, where's that going to put you? 2/3 of the way is going to be, what's about to here? Remember, when we've done a lot of problems before, the important thing was in which quadrant was the terminal side of the angle. So 2/3 of the way to here is going to put me in the 3rd quadrant. That's not a very accurate picture, but the key is it's in the 3rd quadrant. I made it go a little too far here. That's better. Well, it's not much better. Okay. Now what about 5 pi over 3? Again, same thing. Think of this as 5/3 pi. Or if you think of 5/3 as 1 2/3, so it's 1 pi plus 2/3 pi. That's the way I'm really thinking of this, right? That's 1 2/3. This is 1 pi plus 2/3 pi, right? That's the way I'm thinking about this. So when you do sketch the angle, you have to go at least 1 pi, which puts me here, right? That's pi. And then it's another 2/3. 2/3, right? Pi radians is another halfway around. Go 2/3 of the way. So it's 2/3 from here to here, which puts me roughly here. Right? So if you break up the fractions, as an improper, as a mixed numeral, right? 5/3, think of that as 1 2/3. So it's 1 pi plus 2/3 pi. 1 pi takes me here, and then go 2/3 of the way to there. So there's a rough sketch of 5 pi over 3 radians. Okay, so let me go back to what we were kind of talking about here, right? Off the top of your head, could you tell me how many radians are in 17 revolutions? So if I went around 17 times, how many radians would that be? Well, it's just 17 times 2 pi. That'd be 34 pi radians, wouldn't it? Okay, so 17 revolutions is 34 pi radians. Okay, without spending any time, what's 17 revolutions in degrees? My guess is you've reached for the calculator, right? Notice I didn't need the calculator to come up with 34 pi. Now, if I wanted to get an approximation, yeah, I would. But people always say, well, there are various reasons for using radians, but also it's keeping the number small. Remember when I mentioned it in several videos back about if we did everything in inches for length, imagine the highway signs, from here to Baton Rouge, it'd say Baton Rouge, I don't know, 3 million inches. I mean, the numbers would be unwieldy. Think what's happening here, right? 34 pi, I mean, isn't that big? What is that, 100 and something, 100 and change, right? But in degrees, 17 revolutions, that's 17 times 360. The numbers are getting unwieldy. So another reason to use radians is just, it keeps the number smaller if you have multiple revolutions. Okay, so hopefully you have a decent feeling for radians here. Now these last two problems are problems we have done before, but we did them in degrees. It always amazes me if it'll be the exact same problem we did before in radians and students don't know how to do it, even though we already did it in degrees. It'd be like if I gave you a solve a right triangle problem and I listed the size in feet, and then I did it again and I listed the size in inches. The procedure's the same. Just because the units are different doesn't change the procedure. So the first example here says, let's find cosine of 5 pi over 6. Again, think of that as 5/6 pi. So I'm going to think of this in radians, and it says give the exact answer. So this is not punched in the calculator. All right, what did we do first? If this were given in degrees, suppose it said, find the exact value of, I don't know, cosine of 315 degrees. What would you have done first? You would draw a picture of the angle. That's what we just practiced doing. So where is 5 pi over 6 radians? Think of that as 5/6 pi, which is less than 1, right? 5/6 is less than 1, so that's less than 1 pi. 1 pi is here, so 5/6 is almost to here. So if you chop this up into 6 pieces, you're going to go through 5 of them. Again, this is not necessarily to scale, but okay, so here's 5 pi over 6. The key is we're in the second quadrant, right? It's more than half pi, and it's less than 1 pi, so it's somewhere in the second quadrant. Okay, what would you do in the next step? What we do in degrees? We picked a point on the terminal side, we made a right triangle out of it. Okay, then what do we do? Well, we need to find the sides of the triangle to figure out the cosine, but what do we do next? We know the angle is 5 pi over 6. What's the reference angle? We always found the reference angle. Well, all the way to here, halfway around, is 1 pi. We've used up 5/6 pi, so that's pi over 6 left, right? 5/6 and 1/6 pi is 1 pi. Okay, but again, remember pi over 6 is 30 degrees. This should not surprise you. It said find the exact value, so you know it's a special triangle. So this is your 30-degree angle, so it's a 1, 2 square root of 3. Those are the 3 numbers. 2 is the largest, so it goes on the hypotenuse. Of the remaining 2 numbers, 1 is the smaller of the 2, which means it goes across the smallest angle. That's the 30, that's the 60 degrees. So the 1 goes here, and square root of 3 goes here. And then remember, once you put your numbers on your triangle, what was the step you need to remember to do? Check for negatives. The root 3 is negative. Because in the second quadrant, x is negative, y is positive. We could do all 6 trig functions now, but they only ask for 1. What's the cosine? The adjacent over hypotenuse, x over r, minus square root of 3 over 2. There we go. This exact same problem we've done before. We're just doing it in radians. Okay, so what's the procedure? Sketch the angle, draw your triangle with a vertical line for the other side, find the reference angle. If it says exact value, it's either quadrantal or special triangle, so you knew this was either going to be the 30, pi over 6, pi over 4, or pi over 3, the 30, the 60, or the 45 degrees. And this pi over 6, which is 30, put in your numbers, okay? Now the last one's similar. It says find the cotangent of negative 5 pi over 4. Again, give the exact value. Again, we did these problems before in degrees, so the procedure is exactly the same. Let's sketch the angle. Now, how do we think of this minus 5 pi over 4? Think of that as minus 5/4 pi, or think of the 5/4 as 1 1/4, as a mixed numeral. Okay, so let's sketch that angle. Now, that's 1 1/4, and it's negative. So negative 1 pi takes me to here, halfway around. And then we still have another negative, still continuing in that direction. How much is a 4th pi? Right? You could remember that's 45 degrees, or just say, go 1/4 of the way to here. Well, that's easy. 1/4 of the way to here is halfway to here. So it's here. We're in the second quadrant again. Okay, so we make our right triangle with a vertical line. And now we need to find the reference angle. Well, we already did, basically. Right? I went minus 1 pi here. I had a 4th pi to go. So that's pi over 4. 45 degrees. So remember, the numbers on our special triangle are 1, 1 squared to 2. The legs have to be the same. The hypotenuse is √2. And again, x has to be negative. So what's the cotangent? It's what cotan is what side over what side. Remember, it's x over y. It's adjacent over opposite, so it's minus 1 over 1. Okay, same procedure as this one. The only new thing is thinking of where this angle is in terms of radians. It's not so hard. Okay, just practice with it and you'll get better at it. Again, in the next chapter, everything's done in radians, so you've got to avoid this. I don't want to learn it. I like degrees. You can't, don't resist it. Just practice with it and you'll get a good feeling for it. Okay, that was that section.